We're back. I'm going to tell you about a geometric series in this video. It's a series you might be familiar with. You studied it probably a couple years ago, but maybe you haven't seen it since. So maybe a little refresher would never hurt everybody. So let's just do a little thought experiment real quick, shall we? So let's pretend you're sitting on one side of the room and you need to get to a sandwich on the other side of the room. In order to get from one side to the other, you gotta cross to the halfway point. All right. So let's say you move to the halfway point. Now, to get from that halfway point to the sandwich, you need to go to the halfway point again, and then to the halfway point, and to the halfway point, and half, and half, and half, and half, and half. Technically, you're never going to get there. You're never going to get to the sandwich. And that is really, really, really hard to take. I mean, because I love sandwiches. So this is Zeno's paradox. Zeno was around a long time ago, before video games, so he had a lot of time to think about stuff like this. And it drove him insane because he said things like, well, if you can't get from one side of the room to the other side to get a sandwich, then you can't even move from where you are. Because to move anywhere means you have to cross a measurable distance that has an infinite number of halves. He says, well, all motion then is an illusion. Ooh, what a psycho, right? Because obviously I'm going to grab the sandwich and it's going to be gone before you can blink an eye. Because he didn't know about calculus. The ancient Greeks didn't really know about limits. They were big on geometry, so they loved like the geometry. Now, yeah, we're talking about geometric series, so funny how that all works out. Naming conventions and everything. All right. So we know that Zeno is full of garbage because if you take a half and you add a fourth and you add an eighth and you add a 16th and a 32nd and so on and so on and so on, eventually you will lead to one. This is an example of an infinite geometric series. And it's geometric not because you can draw squares and stuff, but the fact that there is a common ratio between the terms. See how the terms just decrease by a factor of 2. You multiply by a half and you get from one to the next. So that's what tells us it's geometric. There's a common ratio between the terms. So this ratio R, as long as that ratio is between -1 and +1, exclusive, might I add, then the geometric series will converge, which kind of backs up what we talked about last time about the nth term test, that if the ratio were equal to 1 or bigger than 1, right? If you continually multiply by 1, you end up the same value. And if that value is not 0, then your series is going to diverge. If the common ratio is bigger than 1, well, if you multiply by something bigger than 1, well, then it's just going to get bigger and bigger and bigger. So the limit of a geometric sequence whose common ratio is greater than 1 is infinity. Well, last time I checked, that's not 0. So that series is also going to diverge. And if you think about it, it'll work with negative values too. It's just that the values will bounce further and further and further away, and it's going to end up diverging. If you don't believe me, here is I read a book called Journey Through Genius, and it was brilliant. I strongly recommend it. But in that book, the author talks about this very geometric series. Like, okay, let's just think about a geometric series. So take a look down here. Let's say a geometric series is r plus r squared plus r cubed plus r to the fourth, et cetera, et cetera, et cetera, et cetera. And that's just like infinitely long. You see how the common ratio there is r. Well, we want to know what the sum of that ratio is. We've declared that it's going to converge because that common ratio is between -1 and 1. But what is the sum? So if you let the sum S B, the geometric series, r plus r squared, etc., and multiply both sides by r, you get r times s is r squared plus r cubed plus r to the fourth, etc. Just the same series without that beginning r. Well, do s minus r times s, right? So check it out. It's r plus r squared, r cubed, but then you subtract all the higher powers of r, so you just end up with r. Well, that means that s times 1 minus r is equal to r. Thus, the sum s is r divided by 1 minus r. Now that's kind of a quick proof, not really a proof, but it's what the author called a 17th century argument. This is what the people who kind of began the ideas of calculus, how they would have treated an infinite series like this. And it works, but to modern mathematicians, it's a little simple. But hey, it works for me because I'm pretty simple too. All right, so a geometric series sum. Here you go. This is big down here. If r is between -1 and 1, then the sum of the geometric series there, this time starts with a. Notice there's a little bit different. A is just a constant. So a plus ar, etc., is going to be equal to a divided by 1 minus r. Now make a note, because that's just the first term divided by 1 minus the ratio. So no matter how the geometric series is packaged, if you've identified it is a geometric series by figuring out what the common ratio is, r, and you can know what the first term is, then the sum of any geometric series is, well, any convergent geometric series, is the first term divided by 1 minus r. Easy as you like it. That's it. So let's see some examples of how that plays out. So here is a geometric series, 1 plus 2/3 plus 4/9 plus 8/27. And you can probably sniff out what the common ratio is, right? To get from 1 to 2/3, you got to multiply by 2/3. To get from 2/3 to 4/9, you got to multiply by 2/3. To get from 4/9 to 8/27, you got to multiply by 2/3. The ratio is 2/3, which it falls in the good range, right? In between -1 and +1. So the answer is going to be simple here. We need the first term divided by 1 minus the ratio. That's easy. So the first term is 1 divided by the quantity 1 minus 2/3. Well, that's 1 divided by 1/3, which is 3. So the sum of that infinite geometric series is 3. Cool. It's pretty rad. Take that, Zeno. All right, here is another one just to get you another look. All right, so here is one that is packaged in summation notation. Okay, so the sum from n equals 2 to infinity of 5 over 4 to the n is what? Okay, so you may see how you got some exponential action there, right? 4 to the n down there in the denominator, right? Exponential functions also match to these geometric sequence terms, right? Because we're just multiplying by the same value repeatedly. That's an exponential function. So 5 over 4 to the n, what are we multiplying by repeatedly? Are we multiplying by 5/4 repeated? No. We're multiplying by 1/4 repeatedly. Can you figure out what the first term is? Well, it's when n is equal to 2. And if n is equal to 2, the first term is 5/16. Now, if you don't believe me there, and you can't sniff that out by looking at this Greek action here, then you're totally allowed to write things out. In fact, that if it helps to write it out, write it out. And if we start at n equals 2, you can see the first few terms there: 5 over 4 squared, 5 over 4 cubed, 5 over 4 to the fourth. Then it's maybe a little bit easier to see that the ratio is 1/4 with the first term of 5 over 16. So boom, you can pop it into the first term over 1 minus r formula, work it out from there, and you see This is going to be 5/16 divided by 3/4, which is 5/16 times 4/3, which is equal to 5/12. So that infinite sum is 5/12. Pretty neat. All right, let's see another one. Here's a pretty cool example, right? These repeated decimals. And you might know what to do with repeated decimals already, but maybe you don't. So could we write the repeating decimal 0.21212121? Could we write it as a rational number, like a number divided by another one where you can't simplify it anymore? So P divided by Q, where P and Q are mutually prime, just fancy words for a totally reduced rational number. So here we go. So maybe this is a little curious, like how are we going to do this with geometric series? Well, you can think about that as 0.21, and every time you see a 21, it's an extra 100th deeper into the decimal. So the original 0.21, right, is 21 over 100. The next 21 is 21 over 10,000. The next 21 you see in the decimal is 21 over a million, and then 21 over 10 to the 8th, and 21 over 10 to the 10th, etc. Oh, you see it? Look at that, right? That is an infinite sum where the ratio from term to term to term is 1 over 100. Well, 1 over 100 is in between -1 and +1. Therefore, this will converge. What will it converge to? Check it out. It's the first term divided by 1 minus the ratio. So 21 over 100 is our first term. We'll divide by 1 minus 1 over 100. So 21 over 100 divided by 99 over 100 is 21 over 99. Well, dang it, I'm an idiot because I can reduce that. And I can reduce that. It just dawned on me. I could divide both sides, everything by 3 there, so I can make that 7 over 33. So don't comment in the YouTube comment section that I'm a moron. Well, no, now you will. Dang it, I just told... Why did I do that? Yeah. Oh, and by the way, while you're commenting that I'm a moron, that I left that as 21 over 99 after I made a big deal about P and Q being mutually prime, go ahead and hit that like button, subscribe key, whatever the heck it is, so you don't miss any new videos. I don't know. All right. One more time. One more example here, just for you guys, just to take one with you. So take a look at the red one down there. We got 3.5 and a 12th and a 72nd, etc., etc. And then the green one, 4 minus 4/9 plus 4 over 81 minus 4 over 729, etc. I got to know which sum is bigger, which is basically just like a 2-for-1 deal. This is 2 problems for the price of 1. I got to find both sums, and then I compare the values. So the red one, right? Can you sniff out what the ratio is? You probably already did. Ratio is 1/6. That means it's going to converge. What's the ratio for the green one? Yeah, that's right. It's -1/9. Is that okay? Sure. -1/9 is between -1 and +1. We're good to go. Let's take these to the formulas. First term over 1 minus the common ratio. So here we go. That means, look at that, it's all worked out for you. The red one is going to converge to 18/5, and the green one is going to converge to 18/5. They're the same. I tricked you. Ha! I gotcha. You were about ready to pick one of those, and they're exactly the same value. Cool. The power of geometric series. They're so fun. They're so fun because they're so cool, and you can treat them in so many different ways. There's some great problems coming your way. If you're in my class, you're going to get some great problems. If you're not in my class, go look for some awesome geometric series questions out there because there's a ton. So I'll see you next time. Bye.